These are precursors. Okay, so the major topic, what we did is, am I audible?
Yes, you are audible.
Hello.
You are audible.
Okay. Yes. Please interrupt me whenever you, because these topics are slightly new. So my major research, what we are going to discuss is lithium excess cathode. These are not conventional layered cathode. These are advanced cathodes. So in short, lithium excess cathode, as the name suggests, is something when lithiums are in excess. It's simply for understanding, we can understand as a lithium, which is certain amount of excess than its conventional amount, like nothing like 1 plus X. It could be considered as lithium excess cathodes. But overall, whatever battery we choose, there are three major problems or issues in the batteries. The first issue is voltage hysteresis. The second could be the capacity decay. And the third could be voltage fades. These are the major crucial decay issues which battery researchers are struggling. The first one is the voltage hysteresis. The voltage hysteresis could be defined as a phenomena in which there is a path difference between the charge and discharge. What does it mean exactly? When we charge, lithiums are extracted from the crystal structure. When lithiums are extracted from the crystal structure, the neighboring transition metal gets a time to move to fill those vacancies. But while discharge, when lithium returns to its original position, the transition metal do not get back to their original position quite often. And in that case, the lithium need to find a different path to come back to its original position. This was much more literal definition of voltage hysteresis, because I know like many of these people might be knowing, but many of the research needs to know. So the path difference creates voltage hysteresis. The second is capacity fade. We often see that when we buy a new phone, after certain charge, we need to charge it frequently. This so happens because most of the cathodes are having polycrystalline, or they are mostly made up of LCO batteries, which have a polycrystalline. A polycrystalline material is a material which has a large grain boundaries or many grain boundaries. When we have several charge and discharge, these grain boundaries are experiencing a stress. When they are stressed, they break apart. When they break apart, the presence of the electrolyte present inside that, they enter into that, and they start creating a stress inside the material. When we further charge and discharge, they get frustrated and they get strained and they finally get ruptured. When they get ruptured, our capacity fails. Quite often, we also see that our phone batteries often do not get close to 100%. That is what is known as voltage fade in batteries. So voltage fade usually happens because the transition metal and lithium ions get swapped up. So the lithium do not get its original position occupancy. That causes the voltage fading issue. So what I mean to say, these are the major issues, whatever battery you choose, whether it is lithium-ion batteries, lithium oxide batteries, any batteries. So researchers can take this as a stepping stone for their research activities. Okay, how could we make a battery structure resilient to these damages? So this was my driving factor. Okay, so research, what I believe, what I have learned from Dr. Amit sir and Bhattacharya sir, they should be simple so that it could reach to common man. So there are different methods of synthesizing battery material, like there could be solid state, there could be chemical route, or there is any like hydrothermal or solvothermal. But I prefer solid state reaction. Solid state reactions are nothing but you just mix up the precursors in a certain amount or dedicated amount. Ball milling is nothing but making them homogenize. To better homogenize, use some solvents like acetone or ethanol, and then dry them, and then optimize the temperature by keeping them in a box furnace or tube furnace. It depends entirely upon the researcher. I usually prefer box furnace. So we made a material, say name it as a like LRNOD. For simplicity, let us make it D. So the doped material. So once we dop the material, the next procedure, what could be whether our material was really formed. So for that, we need to go to excuse me. Anybody interrupted me?
No, you continue.
Okay. So the next, am I going correct, Prof. Amit sir? Or should I go much more faster?
No, continue. No problem. The speed is okay.
Okay, thank you. Thank you, sir. So the first one is compositional. I want to stress because my fellow main Indians should learn as much as I know. So it could be much more beneficial to them as well. So how the research should be carried out in our lab. So to go to confirm whether your material is actually formed, we have different set of analytical techniques. But the reliable technique is ICP-MS. ICP-MS, when we reached to ICP-MS, we found that, okay, our certain elements, lithium composition, aluminum composition, nickel composition, ruthenium composition were slightly different from what the theoretical composition we took. And it happens because theoretical composition and experimental composition, there is a difference. And whenever you often encounter to see a paper for review, you can easily recognize that there is a flaw or not. If it is exactly same, which is impossible, highly impossible. So if you see that in parenthesis, what we see that our theoretical composition, and this was the experimental composition. So we confirmed that our experimental composition was close to the theoretical composition, and we synthesize our material in the same composition what we want. We can also go, because there is no set of experiment which can confirm all the results, but that's the reason we need to go for one or two confirmatory techniques. The other can also be taken from SEM or HRTEM both. So site selective HRTEM images can also be taken to confirm the elemental distribution to make it 100% that your materials are really formed. So moving to the first fingerprinting, that is XRD. XRD gives the crystal structure geometry, that what the crystal structure your material occupies or it has. So in our case, we synthesize two materials, LRNOP, the pristine, the P stands for pristine, and then we dop with aluminum. And for simplicity, let us mark it as a PND. So for that, we need to have a crystal structure which is already reported. So the reported crystal structure we took is LRO, like lithium ruthenium oxide. Many of you battery researchers might be knowing that. It has a monoclinic structure. So, and we need it for referencing because we cannot, since these materials are like we approach to XRD to confirm, we need certain references. So we chose this as a reference because it was close to our material. There are other techniques. When we dop, there is a Rietveld refinement phenomena. Rietveld refinement explains where is your dopant sitting. So for that, we see these are observational parameters. We need not to go into details, but Rietveld refinement explains that what happens when you dop, at which lattice site your material exists. And these are nothing but these are LRNOP and this is doped one. So what we could see that the fitting is close to like better, like closer to 5 or 1 to 5. It is appreciated, but I couldn't make it. But researchers can make it too close to 1, so that it is good. So, but what information we could extract from the lithium-ion battery XRD profile, that there is a peak around 63. This is a major peak which confirms that your battery is layered material or disordered material or any other type of material. So if peak splits around 63 degree, like 018 or 110, it is splitting means it is a layered material. If it is merged, it is a disordered material, just for information. But there is a question that could be raised here, that why do battery materials are often in hexagonal structure? I'm not expert in crystallography, but we must know the basic or the fundamental things which are involved in the crystal lattice of our research. So primarily, lithium-ion batteries occupies the hexagonal structure simply because it gives you the maximum storage capacity. So, okay, now as I explained those three issues, now how to mitigate them? So to mitigate them, we took the help of the DFT, density functional theory, and we designed the crystal structure. So what the idea is, usually why do battery explodes? In short, battery explodes because the oxygen in the crystal lattice moves away from the battery surfaces during charge and discharge, and they catches fire. So the idea should be to stop those oxygen removal from the crystal structure. So what we could see that during charging, when lithium leaves, we could see that oxygen approaches in the radial direction. When there is no interruption, oxygen has a propensity to attract to the other oxygen and evolve from the crystal structure, right? When we dock with certain element like nickel, we could see that lithium, ruthenium, it is N stands for nickel. So when we docked with the transition metal, what we could see that the radial distance started slightly increasing from 2.39 angstrom to 2.56. But what interesting factors happened when we docked with aluminum? We could see that the radial distance increased to a certain extent that the oxygen takes a long time to fuse towards each other. One could see this animation that the radial symmetry is now broken. So when we break the radial symmetry, oxygen do not approach in the same direction or the same radial distances, and they do not dimerize and they do not leave the crystal structure. As of now, I think I have made clear what exactly is concept of distorted octahedra. Usually, like when we dock, we try to distort the octahedra. The more the distortion is, it's not better. But to a certain extent, it should be in certain extent that the radial symmetry must be broken. The band diagram could see that when we dock with aluminum as 3+, it has greater overlap with oxygen. And that's the reason we would be explaining why the concept of aluminum doping helps in the batteries. Like we could see that NCA, nickel, cobalt, aluminum oxides. NCA is a commercialized material, like Nissan batteries, they have NCA. So the concept of doping we will be explained hereafter in much more details. But as of now, the foundation is clear. Okay, so taking one by one the issues. As I mentioned earlier, the voltage hysteresis. One could see that LRO has a higher gap between charge and discharge, like first cycle charge and second cycle discharge. So there is a gap. But when we dock with nickel, we could see that this rift is getting lower and lower and lower. But in our case, when we docked with nickel and aluminum, they superimpose. So one could easily identify the voltage hysteresis gap is reduced to a larger extent, that now first cycle charge and second cycle charge, they superimpose completely. So how do we evolve with much more support? So we could take dq by dv plots. dq by dv plots are nothing but differential plots, which explains in details how charging and discharging happens. So when we talk about lithium ruthenium oxide, when we see the charge discharge plots or dq by dv plot, we see that there is an oxidation peak of ruthenium. Many of the battery researchers might be knowing about this. This material has an oxygen redox. I will explain in my later slide what oxygen redox is, but oxygen redox is nothing but when the contribution also comes from oxygen apart from transition metal. So we could see the other peaks are oxygen redox. Even in the second cycle at high voltage, oxygen redox usually happens at the high voltage, near about greater than 4.4 volt. We could see the second cycle has oxygen redox. It's not bad that oxygen redox should not happen. It is good that when oxygen redox happens, they tends to have more capacity. But this is also vital to because since oxygen is involved in the reaction, it has a propensity to leave. That's the reason, despite having the higher capacity, one could see around 300 milliampere hour per gram, it has a higher voltage hysteresis. But when we docked with nickel, we could see that from the second cycle, the oxidation is suppressed. Finally, when we dock with aluminum, we find no oxygen redox. Though it is bad that we encounter only 250 capacity, but what it means that though there should always be, a researcher should always think about trade-off, that what could be minimized and what could be maximized. So in this case, even if you get more capacity and if you buy a phone and it gets faded in 1 year, you often don't like it. But if you buy a phone which lasts for 4 or 5 years, you definitely like it, simply, right? The basic idea what we chose is, though we compromise with the capacity, we definitely should not compromise on the longevity. And that is what this is what our idea when we buy any electronic gadgets, that it should work for longer period. It should serve us for longer period. Okay. So as I explained earlier, that how voltage fades happen, like voltage fade usually happen, just to remind, when transition metal enters inside the lithium structure. So one could see that in lithium ruthenium oxides, this is the pristine state, like bare state after synthesis. These bright spots are transition metal. These dark spots are lithium layer. As a material expert, we should know that the bright spots would always be the transition metal. Dark spots are lying lower in the HRTM images, so the light doesn't come from them. So they appears to be darker. Means like they could not be imagined in the HRTM images. So the dark spots are lithium there. And moreover, they're also small. So they could not be captured by the lithium, the HRTM ion beam. So, but ideally, these are the bright spots are lithium, bright spots are, pardon me, it's transition metal, and dark spots are lithium layer. When we cycle them, we see immediately, though we had 300 milliampere hour per gram, the crystal structure deteriorates. When we docked with nickel, we could see there are some brighter spots still, but it is certainly lesser than that. But in our aluminum dock, what we find, we could see that there is no bright spots in the dark spots of here, like no transition metal in this layer. It confirms that the migration of transition metal into the lithium layer during charge discharge was greatly suppressed. This phenomena, many of my battery researchers might be knowing that this is also known as transition metal dissolution. Dissolution, it usually happens for Mn. Like in commercial batteries, during charge discharge, many of the transition metal get dissolved in the crystal structure, like in electrolyte, and they form other complex reactions, which we are not going to deal with. The idea is how to identify that your battery material has a good performance. Now, coming back to charge discharge cycle, we could see there is a large span, like there is a large voltage decay or capacity fading here as well. And in aluminum dot, we could see the arrow here is very small. Interestingly, some could raise question that why did it happen that the charge discharge in nickel dot is higher? Where the answer could be the ionic radii of lithium Li plus and the ionic radii of Ni2 plus are identical. So it also happens that nickel occupies, in spite of doping, nickel occupies exactly the lithium site. And because of nickel doping, the anti-side defects increases. That's the reason people are also aware that they should lessen the nickel content in the commercial batteries. But nickel helps in stabilizing the crystal structure. So again, here comes a trade-off. Like nickels are must, but nickel has to be optimized. This is what the research should go on. Again, the capacity decay. As I mentioned earlier, the capacity decay is more or less directly related to the integrity of the crystal structure of the grain boundaries or grains. So we took the cycle images under HRTM images. And what we found interestingly that aluminum dop has integrated crystal structure even after long cycling of after 100 cycles. But we see in nickel dop, there are some pits on the surface structure. These pits are corrosion. Like it, because in presence of electrolyte, HF can corrode this one. But in case of aluminum dop, we find the crystal structure or the grain boundaries or grain surface is very pure. It means it has not been corroded. And this is one reason why your material could improve the performance, or it you can extract more electrochemical performance of your material. Okay, as Professor Abdul Karim sir explained about the impedance data, what we could get from the impedance data. Impedance are really important, and the Nyquist plots are really important to know what exactly how ions behave in your crystal structure. The semicircle here could be perceived as charge transfer resistance. So what we could see the pink color, it has a smaller semicircle. The smaller semicircle reflects lesser resistance for the charge transfer resistance. Interestingly, what we could see that even after 10 cycle of charge discharge cycle, the cyclic resistance or charge transfer resistance does not increases. The other half denotes the solid electrolyte interface boundaries. So from this graph, we could see that RCT decreases, SCI decreases. When RCT and SCI both decreases, capacity fade also decreases. And that could be reflected here. We could see that capacity is almost or reaching 200%, or it's greater than 99%. Here it could be reflected. Why the material behaves more, like why did our material has a better performance? We could see that our material performed better than 99% for more than 130 cycles. And that is quite appreciable. Battery researchers should also perform their electrochemical performance at high temperature, because all the batteries are not going to operate at the room temperature. They will be engaged at high temperature also. So for that, we took performance at 60 degrees C. Interestingly, what we found that this even at high temperature, our doped material has better performance. It means that aluminum doping, the chemistry of aluminum doping will be explained by DFT in the further slides. But as of now, what we could explain that we could see that LRO has a huge capacity decay. Nickel, on the contrary, has lesser amount of decay, but greener doped one, it shows that okay, it has better capacity. It is even at the 60 degrees. The reasons I will be explaining later on. We use advanced or state-of-the-art characterization techniques, particularly hexase. Hexase, it has two major aspects. It has zanes and exapes. These zanes and exapes gives you the radial symmetry and the radial distance information, how the crystal structures actually behave inside the crystal structure. I may appreciate any questions on this because these are the state-of-the-art characterization techniques. So what we believe when we took exapes data, this is exapes data. So when we took exapes data, we found that there is almost similar ruthenium oxide distance in both the material. This is LRNOP and this is the doped one. But again, the questions can be raised that how did you confirm that your aluminum is doped where and is it really doped? So to confirm that, one could, I would need to explain certain things. Like when we take XRD or any data, the decline in the intensity remarks or reflects the defects in the crystal structure. It is a base. So if we see that the intensity in undoped, the nickel intensity is higher. But what happened to nickel in the doped one? We see that intensity of the nickel here is reduced. So what does this reduction exactly mean? This reduction in nickel intensity means that our aluminum is occupied or is occupying or is substituted partial nickel. And we intentionally doped aluminum in place of nickel. The reason I will be, as I mentioned, that nickel is good, but there should always be a trade-off in the nickel composition because again, lithium and nickel share the same ionic radii. So the content of the nickel should be reduced to a certain extent so that we can extract the benefit, but still hamper its demerits. Need not to, these are the fitting parameters. People working on exapes data or synchrotron data, they must be knowing how do we fit. So this will be more crucial when we go later on. Okay, so what happens? Like, as I mentioned, there is no single experiment which proves all of your data. So we need to take multiple experiments assistance. So what we did, and how do we confirm that we have a better crystal symmetry, even after 100, see here denotes 100 cycles. So what we did, this is the nickel dop, this is aluminum dop. So what we found, let us see ruthenium and oxygen bond distance. In nickel dop, after 100 cycle, you see the ruthenium and oxygen bond distance is 2.12. While in aluminum dop, you could see that ruthenium and oxygen bond distance is 2.06. What does it exactly mean? It means that the oxygen is bonded now more strongly to ruthenium due to aluminum presence. It means the propensity of oxygen leaving the crystal structure is less. It will be confirmed even further. Okay, though it looks a little bit complex, but I need to take. So what happens? Let us look on the closer detail on the ruthenium bond distances. We could see that ruthenium bond distance from 2.03 changes to 2.12 in nickel dop. But on the other hand, if we see that the bond distance between in the doped one, considering ruthenium, is very less. It means the fluctuation in the ruthenium coordination or ruthenium environment is very less. So this confirms that, or we can confirm that, okay, the ruthenium environment is stable. But what about nickel? As I mentioned, the nickel is very deleterious or it's dangerous to battery researchers. But at the same time, it is beneficial. So in our case, if we take nickel oxide, the bond distance is long, like its variation is larger, like 2.04 to 1.97. But in our case, if we take any of the nickel distance, they're more or less same, like 2.7, 2.7 or 0.86, they're more or less 7. It means aluminum doping has succeeded in preventing the nickel migration to a certain extent. Again, X-phase is a well-known phenomena. It is often taken because to explore the oxygen reactivity on the surface, because our cathode materials are ceramic materials in which oxygen plays a dominant propensity to leak from the crystal structure or leave the crystal structure. Before going to explain the XPS data, I need to explain certain thing about why do we probe oxygen. The idea behind probing oxygen is the whole idea is to suppress oxygen from the crystal structure. But there are two peaks here, as could be. This is the peak around 529.7 is the lattice oxygen. It is known as lattice oxygen. The peak around 53.9 is known as dimerized oxygen. The central idea is to make this equivalent, like it helps in oxo to peroxo formation, and this is good when your material has large number, like oxygen will always be in a certain position to dimerize and it convert back to its lattice oxygen. And this is the ideal condition, but it really does not happen. Like, see, when we charge, there is a decline in the dimerized state of oxygen. But what happens, the interesting part I need to explain is when we discharge again back, you see there is a great change here. And there is also a change in the crystal structure when we discharge of doped one. But interestingly, what we found, there is another peak shooting over here, is that 528.08. The peak around 528.08 corresponds to the aluminum and oxygen bond. What it reflects is when we have aluminum, it holds back again the oxygen. But in case of nickel, when we discharge it back to its original state after charging, we find that oxygen has released from the lattice structure. It means despite nickel doping, it cannot suppress all the oxygen from leaving the crystal structure. We took the assistance of density functional theory. Please, people can interrupt me. Hello?
Yes.
Hello? Okay, people can interrupt me, no problem. So, we took the formation energy calculation from the density functional theory. So the idea, the basic central idea of using the formation energy is how much a material is stable. It is reflected by the negative formation energy. Like the more the negative energy a material has, according to Gibbs free energy, your crystal will be stable. So one could see that the doped material is more negative. But after a certain extent, it starts exploding. And in reality, it happens that in reality, only lithium extraction of 60 to 70% is allowed. But we extracted lithium to 75%. When you extract all of your lithium, definitely as a material scientist, when you remove all of lithium, there will be lithium vacancies. And when lithium vacancies increase to a certain extent, the crystal will collapse. And it happens in reality. And what we could see that though our material sustained to 75% extracted lithium, after further removing the lithium, it will distort or it will collapse the crystal structure. We also took the Bader charge calculation. Why did we go for Bader charge calculation? Is because we have aluminum doping. When aluminum or electropositive elements are doped in any crystal structure, it has more propensity towards oxygen because it can readily give their electropositive ions to oxygen. Like we could see then in doped one, even in 50 and 75%, it is more negative. It means aluminum has propensity, or in other ways, oxygen can take the electrons from aluminum and can bond an ionic bond. An ionic bonds are stable. When we go for formation energy calculation, the much more explanation can be gained from the aluminum. What we found, we see that aluminum always tries to cluster near the nickel, and that's what confirms that our aluminum was doped in the nickel site. Now we can easily confirm, and many of the reviewers ask the same questions. So this graph or this crystal structure can really explain that why nickel or aluminum clusters to the nickel. We also took COHP calculation. Why are we taking so much of density functional theory calculation support? It is simply because the mechanistic origin cannot be explained from the electrochemistry. So we need to have a strong foundation or a strong extraction of data from theoretical support so that the material can be strongly convinced to research, to like reviewers. So we also took COHP calculation, crystal orbital Hamiltonian population. This explains how your material spins around the Fermi level. Interesting facts about, could be not all graphs are important to mention here. like stress could be given on the aluminum profile. What could be taken from here that even after 50% or in 50% or 75%, I will consider only 50% and 75% for that. Even if 50% is taken, which is almost close to the allowed extraction of lithium, we see that the aluminum does not come closer to the Fermi level. It means oxygen, it is bonded to oxygen strictly. But as I mentioned earlier, that when you extract all of the lithium or nearly moving away from the 75%, even aluminum cannot hold. And it's true, when you extract all the lithium, which is definitely not permitted in the real system, and which is really not possible to extract all the lithium. So it destabilizes the crystal structure. But in short, the aluminum bonds stabilizes the crystal structure. Now we can easily confirm that we have a strong stabilization effect of aluminum, and this material has a strong propensity to hold the crystal structure even for the long cycling. In short, what could be taken? The message takeaway home is the voltage hysteresis was minimized, the capacity decay was improved, and the voltage decay was also improved to a certain extent. This was our first question. I would appreciate any questions on this, because now we'll be dealing with an advanced reaction mechanism, which is known as anionic redox. Before moving to further slides, I would like to explain what exactly anionic redox activity means. Conventionally, it was believed that a battery capacity or a capacity in a battery only comes from the transition metal. But lately, Ruxel group or like the research in Germany found that there is anionic redox activity also participating in your battery material. Anionic redox activity is an activity when electrons compensation or charge compensation also comes from oxygen in addition to the transition metal. As I explained before, that in our lithium ruthenium oxide do have anionic redox like oxygen participation. That's the reason they have high capacity. But when oxygen comes into picture, because since it is gas, it has a high propensity to leave the crystal structure. So it makes the crystal structure fade. So the compromise again has to be made, or a trade-off has to be made, still to use anionic redox, but to make it sustain. And that is what our next goal is. Like here, like it has to be reversible for a long time. And yes, before moving to the further discussion, I would also like to state that though anionic if your material though may not be anionic redox, one can activate it. That is also the good research area. And what we took inactive material, and we activated anionic redox in it and also sustained it. So for that, again, we took the same base material and ball mill for longer period. So when we ball mill for longer period, as I explained, that peak around 63 degrees, they are splitted. So still they are layered structure. So the beauty of this is that even if you have layered structure, when you ball mill for a longer period, like when you control the ball milling time and temperature time, you encounter different crystal structure. That is what the first idea is. So here we dock with sodium. Like here and means it's sodium. So when we dock with sodium, some interesting chemistry popped up. The first one is the radii of sodium, as we know, like lithium, sodium, potassium, they lie in the same group. So the radii of the sodium is slightly larger than lithium. So when we dock with lithium, with slightly larger radii, sodium, there would be definitely faults. That is known as stacking fault. So stacking faults are good. Faults are always not bad. Faults could be good. They can create certain vacancies where lithium distortion could be accommodated. So this is one aspect. This fault and the stacking faults are also beneficial when we do water splitting or energy surface related activities. So this is nothing but like SEM images and TM images. What we found that we see like there is also a change in the morphology. Like this is a pristine material, and we docked with nickel, sodium, the morphology also changes. When we docked with sodium, and when we took their HRTM images, we see there is a defective structure. And these defective structures are nothing but the stacking fault defects arising due to the larger ionic radii of sodium. And this is nothing but HRTM SAD pattern. And this is elemental mapping. again, the basic orientation of doing this is how crystal structure changes in presence of anionic activity. So since, as I mentioned, that when we have oxygen activity, the surface becomes much more dominant for studying purpose. So when we see, I will concentrate mainly on oxygen. How does oxygen parameters changes when we drop sodium? One could see this is lattice oxygen, and this is dimerized oxygen. We could see that there is a larger amount of dimerized oxygen now when we drop with sodium. So what does it exactly mean? When we have excess of dimerization oxygen, your material will be having more of oxygen to participate in the chemical reaction. The additional part will be explained later on. Okay. Now, what exactly anionic activity means? Conventionally, all batteries demonstrate capacity simply coming from transition metal. But in anionic dominated material, the capacity also comes from oxygen contribution. One could see that the capacity was only 200. The same material doped with sodium with higher ball milling has higher capacity. And this was the beauty of the doping materials. One could easily rectify or see here that now we have anionic redox in the crystal structure. But the major problem with anionic redox material is they do not sustain for a long time. Like one could see that they are much more higher than the theoretical capacity. Like theoretically, this material was supposed to give 177, but now the experimental capacity is around 280. So how to figure it out and how to characterize whether your material has anionic redox? As I mentioned, usually anionic redox are activated at high voltage. One could see that they are much more beyond 4.5 volt. When we dop with nickel, they reduce to a lower voltage. On the contrary, like 4.5 to 4.26. What does it really mean? It means that when you dop a material of suitable geometry or suitable electronic structure, you can tune the electronic structure of the material to a larger extent. We could see that when we dop with sodium, the anionic redox, which was occurring at 4.52, now shifted to 4.26. It means that now anionic redox has a dominant role in offering the crystal structure. This sort of information can be taken from our XRD, from the electrochemical data and DQ by dB plots. Okay, and these are nothing but the electrochemical data. Electrochemical data like this is rate test. The idea what we want to emphasize on the figure D and E. As I explained, that when we have anionic redox, you encounter large voltage or capacity fading, and that's what it reflects. One could see that we have definitely there is a large voltage or capacity fading, and it will always happen when your material has an anionic activity. But the idea is how to control that and still benefit from that. So we could see that we have controlled the capacity fading by sodium doping, because in the later part I will explain what does sodium exactly do. Sodium not only does the activation process, it also holds the potential is known as pillaring effect, which does not allow the migration of transition metal when lithiums are not there. So it has a dual purpose. So as I mentioned that the anionic activities are activities apart from the transition metal capacity giving properties. One could see that at higher voltages, anionic dominated species gets active. This graph will be more clear, I guess. So this is a normalized capacity. So one could see that the surge or the drop in voltage in nickel dop is higher, whereas it has a short drop in voltage capacity. So what we contributed that despite activating the anionic redox, we have reduced the capacity fading, and that's what we contributed to battery resets. And how does we confirm that our anionic redox is sustainable? So this mechanism, this scheme will help you to better understand how pillaring effect exactly works. When we charge, we create lithium vacancies. Lithium is in tetrahedral space. So when this space is vacant, any transition metal in the neighboring spot has a propensity to enter into that, right? So when neighboring transition metal enters, it creates a distortion in the crystal structure. So while returning, ideally, the transition metal must come back to its original position, but in reality, it doesn't happen. But what happened when we have sodium doping? When we have sodium doping, even when the lithium moves from the crystal structure, in presence of sodium, transition metal does not have proper space to get accommodated in the vacant space because of presence of sodium. So the transition metal migration does not happen. So now we could see that the sodium has dual purpose. It not only activated anionic redox, but it also forbids the transition metal migrancy. So it has dual purpose. We took machine learning assistance to explain how transition metal and how anionic activity got activated and what is the perspective of crystal structure stability. So usually anionic redox activity happens when we have LiOL configuration. This is known as LiO2 type structures. What does exactly mean? When oxygen is bonded to less labile oxygen, less labile lithium, we encounter more anions in the crystal structure. So when we have more anions in the crystal structure, we could store more charges, and this is the fundamental idea that the battery researcher must thrive to get LiOL configuration in the battery material. This could be achieved by doping, by tuning the ball milling time, and there are several other factors. But the central idea is to get anionic activity, is to get LiOL configuration, because oxygen is now bonded to less electropositive lithium, which has a greater propensity to leave oxygen, so that oxygen is more labile. One could see that when we dop sodium, the fluctuation in the crystal structure, this is nickel dop, sodium dop. One could see that the initial fluctuation, though, was larger. It's simply because nickel have a larger radii. But during cycling, we could see that the fluctuation or layer spacing fluctuations in sodium doping is slightly less. It means that sodium also coordinates to oxygen and it prevents the migration of oxygen. And yet it also has a pillaring effect so that the migration of transition metal doesn't happen. We also took density functional theory calculation to show what exactly sodium does. So when we dop with sodium, we could see the band structures are away from the Fermi level. But in case of sodium, the band structure moves towards the Fermi level. So what does it mean? Shifting of oxygen to the Fermi level, the red color. The shifting of oxygen to the Fermi level simply means that now more of oxygen electrons are available for conductivity. And this is what we proved, that when we dop with sodium, we can translate the oxygen lower lying orbitals closer towards the Fermi level so that more oxygen electrons are involved in the reactions. And this is known as anionic activity participation. And this is need not to explain. This is like what I said, like if you have anionic activity, you may encounter a greater fading. But here we, even for the 50 cycle at high C rate, like 0.2 C rate, we encountered a very stable profile of electrochemical data. And again, this is Nyquist plot. Nyquist plot is again to explain how charge transfer resistance varies. So we could see it has lesser charge transfer resistance in sodium doping. So overall, what do we explain here is when we dop with a particular or suitable element, the chemistry of the material can be tuned up and we can extract beneficial things from the same material. So like RCT decreases, SCI, again, the same concept, lesser capacity feeding. So before moving to, do we have any questions? Hello.
Aditya, I got 2 questions in chat box.
Yes, Professor. Yes, sir.
Questions are from Dr. Sandhya Gupta. She's asking, the first is, what is the crucial challenge in lithium-ion batteries? And secondly is, for environmental safety,
yes,
how to dispose the lithium-ion batteries, and is there any safe alternative of lithium-ion? I think you can answer this question at the end of your talk. Already we are running 12:25. I think we can answer the question at the end.
How long I have still time?
You can wind up within 10 minutes.
Okay, no problem. So the idea of my talk was basically to give a brief or explanatory things that how we can tune exactly the battery materials are. Again, and I will slightly swap it faster. Again, what we thought, see, not all the research and not all the dopings are good. So what we did, we thought of, okay, why not to get benefit of sodium and aluminum both together? But when we did this, we found interesting data that no, when we have sodium and aluminum individually, they perform different aspects. When we do it combinedly, they don't perform in the same. And this is what the beauty of research is, that you don't get what you expect sometimes, and sometimes you get what you don't expect. When we doped sodium and aluminum both, we found faceted structures. And many of the battery researchers or people working on energy material, they know the importance of faceted structures. Faceted structures are very crucial for surface reactivity reactions. Like when you have faceted reaction, a particular XRD planes are much more dominant. Like when we doped sodium and aluminum, we encounter much more defective crystal structures. These defective structures can be beneficial when you apply these battery materials to other applications like energy storage or water splitting. I will show again, need not to show on this. When we use this for water splitting, we found that, see, the same battery material could be used as a water splitting material. The idea was to integrate the concepts like the integration of technology, like the same battery could be used as a water splitting so that the concept of battleizer can come. Like if you invest in batteries, you can also use as an energy harvester, like energy generator rather, as a, I should not say energy generator because energy cannot be generated, but energy can be produced, like it can be converted. Like if you have battleizer and if you tune it properly, you can also do water splitting reactions. And once you consume, once you produce. So this is simply because we encountered faceted structures, and faceted structures have a larger area for surface reactivity or surface chemical reactions, like mainly which happens in water splitting. You could see like there are amorphous zone and crystalline zone, and there are defective zone. It's simply that when you dop individually, you encounter certain different chemistry. When you dop together, you encounter certain different chemistry. So care must be taken to when you go for doping. Okay, I need, because I have many things to discuss, but I think I killed a lot of time. Yes, the second part of the answer, is there any alternative to lithium-ion battery? Yes, definitely. There are other alternative. We are working on sodium-ion battery. Sodium is very eco-friendly and benign to nature. So if you don't want to go for lithium-ion battery, definitely you can go for sodium-ion battery. So this is one topic I can suggest, like one research field I can stress upon, that the sodium research could be taken for the future. And people are moving towards sodium-ion battery. Even we have moved from, even most of the battery researchers are moving from lithium to sodium-ion batteries. So again, since this is unpublished data, so but the problem in sodium-ion battery is, since sodium is very heavy, like heavier than lithium, despite all the efforts you make, you won't be able to compete with the capacity of lithium-ion battery inherently, because sodium is very heavy. So even if the world reaches to ultimate in sodium ion, the capacity will never match to the lithium ion, because definitely the mass of the sodium is very high, but it is eco-friendly. The problem with the sodium ion battery research is also that since it is heavy, the capacity fading is very high. But what we did, we properly tuned it, and we achieved a, like, so far the world best capacity we are achieving in sodium ion battery. Hopefully we publish in some decent journals. And to end up my lecture talk, this is some of our like publications. When I was in PhD, we developed certain materials for water splitting. Again, it was a battleizer. So the idea, what I need to explain here, that though we have battery material, don't stop yourself from integrating to other field, like any other field, like energy storage or optoelectronics or peroxides. So the same battery material can be engaged in any other domains as well. So thank you. This is all my collaborators. Yes. Now I think I have reached to the time, right?
Thank you.
Amit, sir?
Yeah, I can. Can you hear me?
Yes, sir. Yes, sir.
So good. So outstanding. Now the questions. If any participant has any query, he or she can ask. Meanwhile, I got some queries, like as I mentioned earlier, like I got some queries from Dr. Sandhya Gupta.
Yes.
As I asked you already, that what are the crucial challenges in lithium-ion batteries? As you already mentioned, that environmental issues is one of the crucial part as far as lithium-ion batteries are concerned. Secondary, what I understand is financial aspect. Lithium-ion batteries are still costly in comparison to sodium-ion batteries, as you mentioned. Sodium-ion batteries still have a good challenge, I think. Coming into the commercial area, it needs some time to work out that. Okay, the other question was she has asked is for environmental safety, how to dispose the lithium-ion battery.
Again, this see the lithium extraction and deposition, like disposition, is a major hurdle to the battery researchers. That's the reason people are moving towards aluminum-ion batteries. Aluminums are like they are very environmental friendly. See, in short, whenever you enter in a lab, you have hazard because whenever you choose any chemical from the periodic table, it is hazardous to nature, right? None of the materials are safer to the our Mother Earth. But in short, as a researcher, what we could do, we could recycle lithium to a certain extent, to a larger extent before disposing it, right? That is one thing we could do. Or move to some other environmental benign elements like sodium-ion battery. Because sodium, again, sodium cannot stand alone. You have nickel, you have cobalt, you need to use any other transition metal. Cobalt is very toxic. That is the reason people are moving from cobalt-free batteries. Even in lithium-ion battery, people are like depleting. They are like the research interest is moving towards cobalt-free batteries. Again, there is a problem with nickel because though nickel has a high capacity or it offers thermal stability, but nickel anti-side effect with the lithium is the biggest problem. So there will be some problem. But to answer to the ma'am's question is recycle the batteries or recycle lithium to a larger extent before depositing it, like before finally disposing it, or move to a greener technology, like use water spitting to generate and use water spitting with batteries so that you can maximize the output. Like make battleizer, like before disposing to lithium, extract much more of it so that it will be less toxic.
Right.
Again, it is a very challenge. Like world is facing the greater threat of lithium, like.
Right, very. Also, she's asking you to share some research papers on this area of basic batteries, as she is new to this area and she's planning to work on the sodium-ion batteries. Okay.
That yes. I could share you.
My another idea is like somehow if people get succeed in developing the batteries based on sodium ion, I think as you mentioned, the size of sodium ion is a bit higher than the lithium ion. Does it affect on the density as well as the size of the battery, the entire size of battery also?
Yes, sir. Once your tap density is like your tap density depends upon the density of the cathode materials. Like so, when a tap density should be high, but in case of sodium, since sodium is very big, the compactness it bursts. Like when we do tapping, or when we do calendaring, like something like a stout person. When you try to squeeze a stout person, he has to burst somewhere, right? It is something like that.
Okay.
So you could see like though we have the world best capacity. I could show you like in sodium-ion battery, this is the world best capacity in sodium-ion battery. But you see, like there is fading. You could see this capacity.
Yes.
This huge fading. And this is just 0.2 C rate. In commercial, it is 3 C.
Yeah.
If you use this battery in Nissan, which has a like 15-minute charge time, it will nowhere sustain. So this is sometimes it feels like it is fancy. We are moving towards fancy things. But this is all about research. This is we need to. You could see there is hysteresis. There's a huge hysteresis.
But also, like if we are discussing on lithium-ion batteries, and if we are coming with a number of limitations, then there are the alternatives. Because science never stops anywhere. So might be in the coming year we find sodium batteries with other alternates also. So might be possible.
Yes.
Yeah. Any more from any participants? Any more questions from participant side? I think Dr. Aditya, now I didn't find any more questions and there are no hand raises also. So now I should put my gratitude and thanks to Dr. Aditya. So on behalf of IPS Academy, Jhabua, and all the supporting staff who is engaging to conduct this FDP. We are into this process for last 8 days and still 1 day is left with us. Thank you to all. Thank you, Dr. Aditya, being here and accepting my invitation to put your very knowledgeable, very interesting talk on this. So thank you very much. We will be in contact and we'll try to get something new out of this. So,
and then have you done that? Like what I was thinking that since many researchers, I highly recommend them to come to my page or even my email. I would love to be getting in touch with them because we are really working on something very good for our country. I came, I came out of country to learn something so that I can go back to again country and get something out of it. So I'm really working hard to learn whatever things I could, whatever you have given me, the base. I'm utilizing it to maximum so that I could, when we return back, we could work. So even if I am abroad, people can contact me in any capacity, being in collaboration, being for postdoc or any other things.
Right.
I would highly love that.
So I will surely share your mail ID with them. And if anybody has any query, they can put a text to you. And
yes,
is interested to have collaborative work, or if anybody is interested to get something out of Dr. Aditya, they can have. So once again, thank you very much, Dr. Aditya. And from now, for today now, I will close this session. And we'll meet you tomorrow once again, the last talk of this FDP, and followed by the valedictory session. So I request all the participants to be present there during the valedictory session. And we, at the same time, we distribute the e-certificate generation link also after the valedictory session. Thank you all. Thank you, Aditya, being here. And we look forward to have some new out of it. Thank you.
Thank you. Thank you so much. Bye-bye.